Hey guys, welcome back to chapter 14. In this video, we're going to talk about a unique kind of property of water. The discussion that we're going to enter in today is going to lead us directly into pH in the next video. So it's going to kind of seem like an awkward topic to talk about, but know that it's going to aid in our understanding of pH at a later time. So what we're going to talk about is something called the autoionization of water. So we saw acid ionization when we mixed an acid into water. We saw base ionization when we mixed a base into water. Well, as it turns out, water is actually an extremely weak electrolyte in and of itself. So if we have a beaker of water, of just H2O molecules, there's actually some that dissociate and create some ions. So there's very, very few, but there are some ions present. Okay. How few am I talking about? 2 out of every billion water molecules form ions through a process called autoionization. So what does this look like from a chemical standpoint? So if we have a water molecule, it will dissociate, so it's going to be definitely a partial dissociation. It's an extremely weak electrolyte. And it's going to dissociate into hydrogen ions and hydroxide ions. Okay. Well, obviously, this autoionization is happening in the presence of other water molecules. So remember that hydrogen ion will react with a water molecule. So sometimes you'll see this autoionization written as such. Okay, so that extra water molecule there is just indicating that this hydrogen is going to react to form that hydronium. Okay, so this is that. I want to clear this stuff. This is that autoionization of water that we see. Okay. So, in summary, all aqueous solutions contain a little bit of hydronium and a little bit of hydroxide. Okay. Here's just some more pictures of this autoionization process, just in a different format. So, we can write a K equation for this process. Okay, so we've seen Ka for acid. We've seen Kb for base. The K value for this autoionization of water is going to be Kw. Okay, W for water. So it's going to be products over reactants. So our products are going to be hydronium and hydroxide. And our reactants, our reactants are water and water. Water is a liquid, so we don't include it. So if I were to kind of clean this up a little bit, the Kw value is just simply hydronium times hydroxide. And as it turns out, this value is a very, very well-known number. But let's think about it before I share with you the number. Would you expect this K value to be big? Do you think it's forward favored? Or would you expect it to be really, really small where it's reactants favored? What would you expect this value to be? Well, every 2 out of 1 billion molecules do this. So I'm going to expect this value to be extremely small because this is a very reactant-favored process. So this is a very well-known, well-researched number, and the autoionization constant of water is 1.0 times 10 to the negative 14. Okay? So that's just a constant. That's a number that is very well researched. There's your value. All right, so this number has a name. It's called the ion product of water, which we see up here on the top of the screen. Okay. The product of hydronium concentration and hydroxide concentration, so multiplying those two together, always equals the same number. It equals 1.0 times 10 to the negative 14. This number is called, like I said, the ion product of water. When I learned it as the dissociation constant of water. So you might hear me use this term. These two really mean the same thing. This is just the one that I learned. This is what textbooks are calling it now. But they both mean the same thing. So we can use this formula, if you will. We can use this formula to help us understand concentrations of hydronium and hydroxide in solutions, in different types of solutions. So in a neutral solution, we would have the same number of hydronium ions and hydroxide ions. So in a neutral solution, those two values are going to be the same. If one of the values, like we have more of one or the other, that's when we start to get solutions that are either acidic or basic. So this is how we define an acidic solution. We define a basic solution. It has to do with the concentrations of hydronium and hydroxide. So in an acidic solution, the hydronium concentration is going to be greater than the hydroxide concentration. So we'll have more of this, less of this. We can also quantify this. So that's kind of qualitatively, like, here's the relationship. We can quantify this using that K, the dissociation of water constant. So if Kw equals concentration of hydronium times concentration of hydroxide, and that value is always 1 times 10 to the negative 14th. If I were to give you the value of hydronium or hydroxide, you could then determine the other one. So in this example, it tells me that the hydronium concentration is 1.0 times 10 to the third. What would the hydroxide concentration be? So we can use this as just like a plug and chug problem. So I put 1.0 times 10 to the negative third here. I'm trying to solve for the concentration of hydroxide, and I know the product of those two is always going to be this value. So then I just solve for hydroxide. I divide by 1.0 times 10 to the negative third. Whatever I do to the left side, I also have to do to the right side. So the hydroxide concentration in this case is 1.0 times 10 to the negative 11. Okay. So we can use it as a formula as well. And now we have numerical values. So 1.0 times 10 to the negative third is a bigger value than 1.0 times 10 to the negative 11th. So that tells me that this is acidic. We have more hydronium than hydroxide. How do we define a basic solution? So a basic solution is going to be where the hydroxide concentration is bigger than the hydronium concentration. So again, we could go through the same math, solve for the hydronium concentration using dissociation constant of water, and then we could decide which one's bigger and which one's smaller. Okay. So let's take a look at an example. So determine the hydronium concentration when the hydroxide concentration is 2.5 times 10 to the negative 9th. And then for funsies, let's try to decide if this is acidic or basic. And then here's that formula that you would be given anyway. So go ahead and pause the video, see if you can solve this, and then I'll catch up to you on the other side. All right, so let's plug in our value for hydroxide into this formula and then chug our way through it. So we're solving for hydronium. We're going to plug in our value for hydroxide, 2.5 times 10 to the negative 9th. And that's going to equal the dissociation constant, which is 1.0 times 10 to the negative 14th. To solve for hydronium, we're going to divide by 2.5 times 10 to the negative 9th. Whatever I do to the left side, I also have to do to the right side. And hydronium concentration is 1.0 times 10 to the negative 14th divided by 2.5 times 10 to the negative 9th. And we get 0 times 10 to the negative 6. Okay. So now for funsies, we wanted to decide if this was acidic or basic. So we see that the hydronium concentration is greater than the hydroxide concentration. So this would turn out to be an acidic solution. I know this because hydronium is greater than hydroxide. So this is one way to determine the hydronium concentration. In the next video, we're going to explore what does that even mean. Like, great, the hydronium concentration is 4.0 times 10 to the negative 6. That doesn't really mean much to me. But we're going to apply it so that it does mean something to you. I hope you guys found this helpful.